Hi, I'm Scott Vaughn, and I'd like to introduce Alexis Andrulonis. Alexis was my student in the spring semester at Montgomery County Community College in an independent study on mathematical modeling and scientific computing. And in that course, we studied a lot of different models, but we spent most of our time in that course on the three-body problem. So this is the presentation that she did at school at the end of the semester, but she actually did a lot more work beyond just what made it into that presentation. So I thought we would go through that presentation, and then we'd also follow up this video with some additional videos later that go into more of the detail of that project that she did in that course. So Alexis, I'll let you take it from there.
Thank you, Professor Vaughn. So as you can see, this presentation is on the three-body problem. So first, a little bit of introduction on the three-body problem. It's a problem in physics and orbital mechanics that looks at the motion of three objects that are influenced by each other's gravity. So as you can imagine, this is a very complicated system, and whenever you slightly change the mass of the objects, their initial velocity, and their initial position, it greatly influences their motion over time, and because of that, we call this problem chaotic. Some history to the three-body problem. A very long time ago, obviously, the ancient Babylonians, the Greeks, and the Chinese predicted solar and lunar eclipses. These involved the Earth, the Sun, and the Moon, so those were the three bodies that they were studying. Edmund Halley predicted in April 1715 solar eclipse using Newton's laws of gravity. Isaac Newton tried to solve the three-body problem, but he was not able to. What he was able to do was to solve the two-body problem exactly, which is just two bodies of mass in space, and he found that those solutions are conics, so parabolas, ellipses, and hyperbolas. After Isaac Newton, there is Henry Poincaré, and he looked at the three-body problem, and he found that there's no general closed-form analytic solutions, which essentially means we can't find exact solutions to the three-body problem. And he described the solutions as chaotic, and all the solutions we get are numerical, which means they are approximations. This is just an old newspaper clipping from 1932 that describes 1932 eclipse as the best viewing opportunity for a solar eclipse in the US until 2017 and 2024. So they really knew in 1932 that we were going to have solar eclipses almost 100 years later, which was really interesting. So here's some examples of the three-body problem. The first one is a Python animation with a given set of initial conditions.
As this is loading, I'll just add in here that Alexis wrote the code for these animations herself, and we hope to go into more of those details in a future video.
You can see the three bodies of mass are moving according to the gravity of each other. It looks pretty random, and a lot of the time we don't really know how it's going to move until we just start approximating and finding these solutions. What the code is doing is it's approximating for every 0.2 seconds or whatever it is to find what's the difference in their position after those 0.2 seconds, and it just keeps going and keeps going. So this is just an approximation. We can also look at this. You can't see the code behind this, but essentially it's a video of just another scenario of the three-body problem, different initial conditions. So I want to start talking about a little bit of the math behind this problem. So to solve this problem, we start with these things called differential equations of motion. So essentially what that means is that we know the acceleration of the objects in terms of their position. And we call this differential equations because the acceleration is the second derivative of position, which means that it's the derivative of the derivative of position. So if you see in this graph, we have a line that's tangent to this curve at the point. And if we take the slope of that tangent line, that will give us the derivative of this curve at this point. So if we do that and we make a graph, which value is the slope at every tangent line that you could draw along this curve. So if you drew a tangent line like this, a tangent line like this, a tangent line like this, all of those slopes would make another curve, and that's the derivative. If we found tangent lines off that derivative curve, that would give us a second derivative, which is the acceleration. So that's why we call it the differential equations of motion. And I'm about to derive these for the three-body problem. We start out with Newton's law of gravity, F equals G m1 m2 over r squared. So m1 and m2 being the mass of the two objects that are feeling the force of gravity towards each other, r squared being the distance between them, g being a very small constant. If we replace force with mass times acceleration, in this case, we're just looking at the force that object 1 feels, which is the same as the force that object 2 feels. But right now we're focusing on the acceleration of object 1. So we replace that with mass 1 times acceleration 1. Same thing over here. If we divide each side by mass 1, we get acceleration of the first object is g times mass of the second object over r squared. Now this is just a scalar quantity right now. There's no direction. R squared is always positive. So if we want to make this into a vector, something that has direction, well, we know that the force of gravity will always be towards the other object. So if we replace r squared with the magnitude of this vector of r21, the vector that points from mass 2 to mass 1, we can do that and still find that same radius. And then if we multiply that by the unit vector of this, so basically it's the same magnitude, it's the same size, but we're just saying we want that vector to go in this direction. But this is actually the opposite direction because we're looking at the acceleration of mass 1, and it's not going this way because otherwise it would be repelled. So we put a negative sign right here because it's going towards mass 2. And then if we simplify that expression a little bit, we get that. So this slide is just taking the expression we derived on the last slide and kind of putting it together to get all of our acceleration equations. So for example, for mass 1, we have the force of the acceleration it's getting from mass 2, but then we add on the same thing because it's also feeling gravity from mass 3. Same thing with object 2 and object 3. We're just adding together those expressions for the acceleration from gravity and the other objects. This is pretty much the same thing, but we're just replacing, we're writing acceleration as instead of just acceleration as the second derivative of position. So in this case, r is kind of just denotes the position of the object. The d squared over dt squared indicates that we're looking at the second derivative. So because of the way we have to solve this, because we're approximating it, a lot of the time it's easier to approximate solutions to differential equations when it's in terms of first order differential equations, which would just be the first derivative. So we rewrite this as instead of saying the second derivative of x position, or I'm sorry, the second derivative of the position of object 1, the second derivative of the position of object 2, and the second derivative of the position of object 3 is acceleration, we write it as the first derivative of the position of object 1 is the velocity of object 1, and then the first derivative of the velocity of object 1 is the acceleration of object 1, and we just write it that way for all of those. So now instead of having these 3 second order differential equations, we have 6 first order differential equations. This is just reiterating that we write the velocity as a derivative of position, and we write acceleration as a derivative of velocity. This is also kind of noting that we're all of these R's, all the V's have little arrows over them, and that denotes that it's a vector. So we can also separate out these equations into one for X and one for Y. So this is just kind of noting that even though it looks like 6 equations, in a way it's actually 12 equations, because we can write this as one in terms of X and one in terms of Y. And of course, we could also write in terms of Z. In most of the scenarios we looked at, we kept Z at 0. We didn't really make that object move at all in the Z direction, so everything was kind of within one plane. So that's why you only see X and Y here. But in a 3-body problem, you definitely can get Z equations for Z. Okay, so I was talking a little bit before about how we need to approximate solutions to the 3-body problem because you can't find exact solutions. So this is what we call numerical solutions. So this differs from analytical solutions, which is where you get a formula or an equation and you can find the exact numbers. So this is just like an example of something you could find the value of X analytically if you were given all the other values, right? But with numerical solutions, you can't. So you're going to get something like this table where you just approximate at all these different values. And because computers can compute things really quickly and really precisely, a lot of the time we will use them to approximate these solutions so we can get the most accurate solutions we can. Because with any numerical method, the more calculations you put into it, the more accurate it'll be. So computers will allow us to do that a lot more quickly. So earlier I was talking about how if you change the initial conditions, the mass, the initial velocity, and the initial position slightly, the 3-body problem, the positions of the objects over time are going to change a lot. And that's something we call chaos. That's why we describe the 3-body problem as chaotic. So if I go into this Python simulation, you can see how these objects are moving in a figure eight, and that figure eight is not really moving much, right? This is pretty stable. It's a clear pattern, and they are deviating slightly, but a lot of that could just be this is not a perfect approximation. But if we were to change the initial position, the initial X position of one of our objects to, say, negative 1.2 instead of negative 1, we actually get something that's very much not a figure eight. And this looks incredibly different from the other one, even though we only changed the positions of one of the objects by just a little bit. So that's part of the reason why it's so important to find approximations that are really accurate, because if your approximation is a little off, then you're going to get very different results for what the positions of the objects are over time. We go back to slide. So I want to talk about a specific type of the 3-body problem called the circular restricted 3-body problem that's used a lot in the real world to approximate these solutions. So the circular restricted 3-body problem, the circular part describes the fact that you have 2 objects that are essentially moving in a circle around their common center of mass. So if you look at this Python simulation, So you can kind of see the green object and the red object are two different objects. And then the white object is their common center of mass. And you can see in the circular restricted three-body problem, they're going to be circling that common center of mass. So the green object is a lot closer, so it's just tracing out that radius. But if you let the simulation run for long enough, you're going to see that they both complete an exact circle, a complete circle at the same time. They're moving around the circle at the same angular velocity. And if you're to draw a line, straight line from the green object to the red object, they're always going to be the white object, their center of mass is always going to be at the same position. So essentially what that means is that if you view this in a rotating frame, if you're kind of spinning as you look at this, it's going to look like all these two objects are not moving relative to their center of mass, that white object. So that's the circular part of the three-body problem is, the circular restricted three-body problem is that you have two objects that are circling their common center of mass. The restricted part of it is that the third object is so small that we consider the two other objects to not feel any force of gravity from that. So that's not a lot because now we only need to look at how the smaller object moves according to the force of gravity from the two larger masses, because the two larger masses are just going to keep circling each other. All right, so some of the significance of the circular restricted three-body problem. Obviously, this is not any real scenario out in space, but it's very close to a lot of real scenarios. Some of these would include the sun, the moon, and the satellite, the sun, the earth, and the satellite, a comet, Jupiter, and the sun, because if you look, for example, with the sun, the earth, and a satellite, we kind of consider that satellite to be the third smaller object because the satellite is so small compared to the sun and the earth that it's not really going to be influencing the motion of the sun and the earth in any noticeable manner. So because we make a few of these simplifications for the circular restricted three-body problem, we can do some specialized math for it. The first thing is what I kind of alluded to earlier, the rotating frame. So in the rotating frame, the perspective is rotating at the same angular velocity as the two larger bodies as they circle their common center of mass. So just to give a little bit of visualization on what this looks like, this video shows you the motion of an object in the circular restricted three-body problem in the inertial frame and the rotating frame side by side. So you can kind of just watch for a little bit and see how that corresponds. Another specialized math part of the circular restricted three-body problem is non-dimensionalized units. So when we're graphing out this problem, it's a lot of the time easier to say the mass is 0.5 rather than the mass is 4.5 times 10 to the 27th. So there are equations out there that will kind of translate normal units to these non-dimensionalized units. A couple of them that are good to note is that the mass of the two objects, they always add to 1. So the way you calculate out their non-dimensionalized mass unit, which is denoted mu, the Greek letter mu, is you kind of compare how much the mass of one compared to the mass of the other. Because of the way We do that. We also put the origin at the center of mass, and I'll talk about this more in a later video, but basically just a lot of things that make it easier to describe this with math. And all these things allow the differential equations of motion to be a lot simpler for the circular restricted three-body problem. Another thing we get from the three-body problem is these things called Lagrange points. So at a Lagrange point, that smaller object is motionless in the rotating frame. So that's points where if you just look at it in the rotating frame, all the forces of gravity from the two larger masses will balance on that particle. So a little bit more about Lagrange points. These are really useful in the real world because we can find quasi-periodic motion about them, which basically means that we can put satellites into orbit around those and have to do relatively few corrections to keep it in the same place relative to the sun and the earth, or the earth and the moon, or whatever it is. L1, L2, and L3, which is short for Lagrange point 1, Lagrange point 2, Lagrange point 3, are all on that line between the earth and the sun. We call these a collinear Lagrange points, and they're unstable, which basically means that if you deviate a little bit from any one of them, you're going to start drifting further and further from that Lagrange point. The other two, L4 and L5, form an equilateral triangle. So if you imagine one line between the sun and the earth, and then the earth and L5 and L5 and the sun, that's an equilateral triangle. L4 is the same thing, just other direction. And those are stable. So if you have a satellite that deviates a little bit from, say, L5, it'll just be pulled back to L5. And this is just kind of showing you. So if you put that smaller object a little bit to the right of L1, that satellite will mostly orbit the mass to the right. But if you put it a little bit before L1, it's going to mostly be around the mass to the left. So that is really interesting case of chaos theory, where you can see how right around the Lagrange points, the initial position of an object is super important as to where it will move later. So in conclusion, the three-body problem can be used to model many real situations in space, and the circular restricted three-body problem is a special case of that, and it's often used to approximate the three-body problem. We're going to be posting future YouTube videos on numerical methods used in the three-body problem, more details about the Lagrange points, and more details about other topics in the circular restricted three-body problem. Just some credits. Most of the information in this presentation is from the paper called Dynamical Systems, the Three-Body Problem in Space Mission Design. Thank you for watching.
Yeah, very impressive. Thank you very much.